Okay, so in the last video, we talked about nucleophile and electrophile and the dynamic that happens between the two. And we even did an example problem where we went through and labeled things as a nucleophile or as an electrophile. And we're focused right now on the world of alkenes. So let me just draw an example of an alkene, just so I can kind of fully flesh this topic out. So let's do CH3, and then we'll do CH, double bond, CH, and CH3 again. All right, so we know by definition this is now called a nucleophile. It does not love electrons. It has a negative area. That negative area is the double bond, so by definition it is a nucleophile. Well, I can bring a reaction into place. I can bring a reaction into place if I have an electrophile, which is electron loving. All right, so let's just bring in something like HBr. All right, so here's the Lewis dot structure of HBr. You're going to look at this structure and you're going to say, oh, wait a minute now, this is not an electrophile, right? I've got these bromine and I've got all of those electrons around that bromine, and I know good and well it's not going to love electrons even more. So by definition, it's not an electrophile. It's not. The bromine piece is not an electrophile. That's not what we're after here. This HBr is a polar compound. All right, this polar compound really changes the dynamic because it's full-blown polar, which means that this is a negative area and this is a positive area. So by definition, we could say that an electrophile is in place, but it's really just on this hydrogen. It's not on the entire molecule because that hydrogen is slightly positive. That slightly positive piece means that it could be slightly electron loving, and if it's slightly electron loving, it meets the definition of an electrophile, and there we go. We have the two pieces of the recipe that makes this thing work. We have a nucleophile, which is a negative area, and we have an electrophile, which is a positive area. Now, in organic, I can show the relationship, the dynamic that's getting ready to happen. And I do that by a curvy arrow. We've seen this before in acid and bases, and that's why I introduced it way back when. It's coming back. I got you used to it. Now we're going to be drawing it even more. So the purpose of curvy arrows, I'm just going to review these rules all over again. I'm going to pretend like everything I talked about back in the acid-base lecture really just went in one end at the other. Curvy arrow rules, number one, you start at the negative end every single time with the arrow. That's the way that you've got to do it. What this means is that we always start at the nucleophile. Now that we know that term, we can apply that term to our new description. So that means I'm going to start my arrow at the nucleophile, the negative area, and this is where I'm going to start it. I'm going to switch my ink, though, to red, just so that you can see this a little bit better. Number two, we always point the arrow toward the positive end. Every single time we point it toward the electrophile. Now we can use our words, can't we? Use your words. I mean, have you ever been around parents, and you might have been one of them. Have you ever been around parents that say that to their kids? Now, use your words. Well, we're using our words in organic at this point. So whenever I draw the curvy arrow, I start at the nucleophile, and I point it toward the electrophile. And I draw it curvy. That's why we call it curvy arrows. But I don't really call it curvy arrows. That's something that I do call it. A lot of people do call it curvy arrow as well. But really what we are showing here is something that we call a mechanism. Mechanism is kind of like mechanics. It's the inner workings. How does it work? That's the question that we have. If this nucleophile and this electrophile come together and they form products, how does that work? What's the details? Gimme. That's the purpose of the curvy arrow mechanism. That's the purpose of the curvy arrows. So this is the first step in the reaction of the nucleophile, which is 2-butene, with hydrobromic acid, which is our electrophile. And I start with the negative end at the end of the arrow, and I point it to the positive end of the electrophile piece. And in doing so, I am showing the mechanism of how this process happens. A couple of things I want to say before we go further, because there's extra steps here that we've not gotten to yet, is that in organic, a curvy arrow, and again, let me switch it to red, a curvy arrow sometimes will have 2 barbs, and a curvy arrow will sometimes have 1 barb. If you see 2 barbs, this represents 2 electrons. That's what we do most of the time. But there is a world of organic that deals with radicals. Radicals is a single electron, and therefore we draw a single barb, curvy arrow to represent that. Please keep in mind, we are not talking about the equilibrium arrow. Equilibrium arrows look like this sometimes, right? These are straight. And believe it or not, in organic, straight arrows are different than curvy arrows. They mean something different. This is the direction of a reaction based on equilibria. This is like Gen Chem stuff, okay? Curvy arrows are representing the flow of electrons. Either 2 electrons, as in the curvy arrow to the left, or 1 electron for the curvy arrow on the right. So we're getting ready to talk about mechanisms. We're getting ready to talk about individual steps of reactions. Now, what happens here? Okay, so let me take my eraser and let me erase some of this stuff that we've been drawing up here, because there's more to this story, and I don't want to erase up at there at the very top. So let me get rid of this, and we're going to focus back on that reaction again. Okay, so if this happens, this double bond is attracted to that partial positive. Well, we can coax that hydrogen to say, come on, I've got a better place for you, hydrogen. Right? You might not feel wanted right now, but I really do need you, and I really do need your support. And I'm negative and you're positive, and I think that we'll be able to get this to work. And hydrogen's going, oh, okay, you know, I've been in this relationship a little bit now, and it's just not quite working for me. Bromine takes everything that I have. Bromine takes every dollar and every cent, every bit of energy that I provide to this molecule. It's just not equal. It's not fair. And this is how bromine has been since I've been in a reaction with it. And it's just not working for me. So hydrogen says, okay, I'll take you up on your offer. If you want to try this out, then maybe I'll just break the bond that I have right now with bromine, because it's not working for me clearly. And maybe I'll just go hang out with you for a while, and we'll see how it works. And this nucleophile says, okay, yeah, I mean, that's what I want. So come around, we'll see if this works out for you, and if you're happy, you can stay. I think that I can treat you better than what that bromine is doing right now. Think of it in terms of a relationship. Again, I think that this helps me in the world of organic. It helps me understand it a little bit better. So when this happens, this CH3 molecule, and again, let me erase that. I don't want to do this in red, not yet. This CH3 molecule, CH double bond CH, CH3, if it does bring that hydrogen on, we got to make a spot for it. Right now, all the spots are taken up. That carbon has 4 bonds. This carbon has 4 bonds. Methyl, hydrogen, 2 from the double. This carbon has 2 bonds. hydrogen, methyl, 2 from the double. And then the final carbon also has 4 bonds. So there's no way right now that this hydrogen can come on board unless that alkene breaks a bond. And if it breaks that double bond, it frees up a location here and it frees up a location there. That's the only way that this is going to work. And that's typically what we say. We say that the alkene will break the double bond. That's what we mean by that. 2 sites of attachment will open up. One to the left, one to the right. And now we've made room for the hydrogen relationship. So this hydrogen says, okay, you're ready for me? Well, you're prepared, and I'm prepared as well. So hydrogen says, see ya, and he leaves. Where do those electrons go in that bond? Between the H and the Br, we draw a curvy arrow to represent that. That curvy arrow goes to the bromine. It was electronegative. It took everything that the hydrogen had anyway. I mean, it was an electron sucker. It sucked every dollar and cent from the hydrogen that it could. Well, we made it happier. Hydrogen said, listen, here's the bank card. I'm out of here. Whatever is used up gets used up. I am not taking part of this relationship anymore. So it is over. See ya. Bye-bye. And away he goes. So now bromine is just left out hanging. Just with some extra electrons right now. Bromine's okay with that. It's electronegative. It's fairly large. It can take care of itself. And this hydrogen is now on this nucleophile. Okay, at this point in time, it really doesn't matter where. So I'm going to draw this hydrogen in purple, and then I'm just going to put the hydrogen right there. Okay? And what we end up with is a carbon that now has a positive charge. Why? Because at this moment, there's nothing there to take it up. At this moment, hydrogen was the only thing that was added. This is the first step of the mechanism. This is how it works. Well, the left-hand carbon has been satisfied. It has everything that it needs for this newfound relationship that it discovered in hydrogen. And the carbon to the right got shortchanged. It said, wait a minute. You told me to cleave this bond in half, and you took the hydrogen. What do I get? Nothing. As of right now, nothing. And this carbon is mad. I mean, you can imagine the carbon is fairly upset at this point because now it really only has 3 bonds, giving it a formal charge of a positive 1. Look at what I did there. I went back to Module 1 and talked about formal charges, didn't I? The carbon's got a bond to the left, a bond to the hydrogen, a bond to the carbon in the methyl side, and that's it. No more. It's shortchanged. It has a positive 1. This was called a carbocation. That was also a term that we talked about in Module 1, wasn't it? We talked about anions and cations, charged species, and here was a carbon that is charged that's positive. A carbocation has been formed in this reaction. Well, good news, good news. This carbon's not out of the water because we just gave this bromine an extra set of electrons, didn't we? It is now fully negative. There are 8 electrons on this, and its formal charge, 7 minus 8, -1. Where did the 7 come from? If you don't remember, that was the valence charges from the periodic table. Look, I brought back another Lecture 1 module topic. It is all wrapping together in a nice little pretty package for Christmas Day. Okay, so here we have bromine that is fully negative and anion. And here we have a carbocation that is positive. What do you think these two things are going to do? and we can redefine nucleophile and electrophile at this point, because guess what, folks? This bromine that has a full negative right now, this is not electron loving anymore. This is my new nucleophile. Right there we go. And this positive charge is not a nucleophile, right? This is an electrophile at this point. And it's an electrophile because it's now electron loving. It has that positive charge that it needs to satisfy. And that bromine is getting ready to man up and get ready to step into this relationship and says, I got it. I got it. Positive and negative naturally attract. This bromine is my nucleophile. It's my negative piece. This is where I start the arrow, and I'm going to point it to the positive piece, which is that carbocation. And ladies and gentlemen, we've just done the next step of the mechanism. We have shown what happens in the next step of the reaction. Step number 1 is at the top. Step number 2 now is detailed down below. So what do we end up with when this begins to form? We have a CH3 group that has a CH and the hydrogen that was there from the HBr. Now that double bond has been broken and we have a CH that was here, but now that carbon also has the bromine from that HBr from up above, and now we finish that off with the CH3, and that is our product. That's our product from the reaction. We have just went through a series of steps that details a mechanism based on the definition of nucleophile and electrophile. And these types of reactions are what we're going to be looking at and studying in the next lecture module. There's going to be one after another, after another, after another. As you can imagine, that's what this thing is going to be. Let's do a little bit of review here. Up here at the top, 1, 2, 3, 4. This is a butene, and this is a 2-butene. Is it cis or is it trans? I didn't give you any details on that, did I? If we assume that it's the most stable, it will be the trans form. Look, I've wrapped in a lecture definition that we've talked about in this module. 2-butene will react with hydrobromic acid. Hydrobromic acid is a polar molecule that has electron distribution that's unequal. I've just now wrapped in lecture 1 definitions and lecture topics. 2-butene reacts with hydrobromic acid because I've got nucleophiles and electrophiles at play. We brought in curvy arrows to show the transition of all of those, and we end up with a product. What's this product's name? 1, 2, 3, 4. This is a butane at this point because it's an alkane. At carbon number 2, I get a bromo group. 2-bromobutane is going to be the name of that product. Not only can I determine the structure of that product, but I can now also determine the name of that product as well. And I have just wrapped in lecture 3 material all over again. All 4 lecture modules are represented in this one simple little bitty example. I told you it was a build-up process, didn't I? And it will continue to be so. And this is the only way that organic will begin to make sense. We have to constantly reach back and grab these old lecture topics that we've been talking about and use them to our advantage. So this is what we refer to as a mechanism. It is basically an electron flow diagram that shows us how nucleophiles and electrophiles interact with each other, and then we can determine product formation based on this. All right? But you have to understand, and this is a common problem that people get wrong in acid bases when I first talk about them, the direction of the arrows. The direction of the arrows are important because they always start at the negative piece and they always point to the positive piece. That is the way this works every single time. Okay? So in the beginnings, what they're going to do with us, and as far as examples and stuff go, is that they will do a pretty good job laying out things on the table. All right, so what do I mean by that? Well, let's do an example of something that they would maybe expect for me to do at this point. So here I'm drawing a structure. That structure has a bromine on it. So in order for this to be neutral, 3 sets of electrons all the way around, right? And then up here at the top with this oxygen, we're just going to keep that as O as of right now. And that means that this is going to be a negative piece. That formal charge is a -1. And then over here to the right-hand side on the product side of the equation, what they're going to do is they're going to draw something that looks like this. Okay, so again, just bear with me just for a minute or two. I'm going to erase that bond, and I'm going to put plus Br, and then this is going to be a minus. And they're going to tell me, just to get me used to drawing curvy arrows, they're going to say, take this example, draw the curvy arrows, and show me how this happens. So it's your job right now to look at this arrow and split it down the middle. And compare the left to the right. What have they done? Okay, what have they done? It looks like there is an extra bond between the carbon and the oxygen, right? It wasn't there before, but now it's there. And then it looks like this bromine has left. It was attached to that carbon, but now it's not. Why? Well, when a double bond forms here, this carbon has 1, 2, 3, 4. It can't have a 5th bond. It can't have a 5th bond to bromine, so bromine's got to go. You know, bromine was that electron sucker anyway. So bromine's got to go. Got to hit the curb. Bye, 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 bye. Take your electronegative self and hit the street. Don't want to see you again. So we have to show curvy arrows illustrating how this process happens. Well, what is that extra line? That extra line is a set of electrons, isn't it? 2 electrons. Look at this oxygen up here. It has 2 sets of electrons. It did have 3. Folks, that's where that double bond was from. This double bond was created because I took an electron set and I moved it here. There's the first step of the mechanism. Now the oxygen only has 2 sets of electrons, and these 2 form the extra line, the double bond, that's between the C and the O. Well, bromine did have 6 dots, but now it has 8 all the way around it with a negative, right? So I'm going to have to take this curvy arrow, and I'm going to have to show it where that came from. Bromine's going to take those electrons between the C and Br. It's going to grab them, it's going to pull them off, and away it goes. And there's the curvy arrow mechanism for this reaction. That's an example that they would like for me to do. It reconfirms the flow of electrons, and that's what we're doing right now. We're getting you used to writing curvy arrows. Let's do another. Let's do CH3, an oxygen with a hydrogen here, and maybe a hydrogen there, and we'll put a free pair of electrons right there, and this thing's going to be negative. And we'll draw an arrow, and we'll do CH3, an oxygen with 2 sets of electrons here, and then a hydrogen, and then we'll do an H+. So the directions are going to tell me, show me how this forms. Show me how we got those products, and use curvy arrows in order to do it. Well, again, you look at the arrow, and you go down the middle, and you compare the left to the right. What have we done? Well, it looks to me like we had a hydrogen on that oxygen, but now that hydrogen is gone. All right, well, did that hydrogen take the electrons with it? And the answer is no, it didn't. How do I know that? Well, that's because this hydrogen's positive. If it took electrons with it, it would be negative. It took those negatives with it. But it didn't. It's just a poor little low hydrogen. That's all it was. So what do we do here in this case? In addition to that, look at the oxygen. There's one set of electrons on it. And here, there's two sets. Where did that extra set come from? Well, that line represents 2. That's where that extra set came from. So I need to draw a curvy arrow that shows how this happens. How do I do that? These electrons that were in that bond, whoop, goes to that oxygen right there. That's all I have to do. That's all I have to do. And in doing so, this arrow shows that that bond breaks. It cleaves. No more glue between the O and the H. That H now goes off on its own, and it's H+. The electrons that were there in that bond are now fully assigned to the oxygen. And that is what gives it its second electron pair. And at this point, it is fully neutral. Formal charge of 0. 6 valence for oxygen. 1 dot, 2 dot, 3 dot, 4 dot, 5 from the line, 6 from the line. 6 minus 6 is 0. Over here, 6 valence from the oxygen. 1 from the dot, 1 from the dot, 1 from the bond, 1 from the bond, 1 from the bond. That's 5. 6 minus 5. It's going to be a 1. That's where that negative comes from. Folks, this is how we show a curvy arrow mechanism. All right? This is the proper order that we do to show the flow of electrons. It always starts at the negative source, which are normally electrons, and it points to the positive sources. Let's look at another. CH3, carbon, CH3. Off of here, we'll do an oxygen, and on that oxygen, we'll do a free pair, and we'll do something that looks like this. That oxygen's so crazy it can't stand it. Over here on the product side, we'll do CH3, carbon, double bond O, and then a CH3, and we'll do an H+ here. All right, so how does this work? Okay, that oxygen, by the way, is charged. What's its charge? Doesn't really matter at this point. That's not really what we're after. We need to compare forward and backward. We need to compare our reagents to our products. If you really want to know, this oxygen's got a 6 valence. 1, 2, 3, 4, 5. There we go. There's the charge on that oxygen. So if we compare the left-hand side versus the right-hand side, what have we done? It looks like we've removed the hydrogen and it's went off as a positive, which means it didn't take electrons with it. And then it also looks like this oxygen had one set of electrons. Well, over here, it's going to have 2 sets of electrons. Where did that second set of electrons come from? From that bond. So I need to show that in the mechanism. So I start my arrow here at the negative source. Whoop! I point it to where it's going to go. That's how the oxygen gets its second set of electrons. That's how the oxygen becomes neutral. And that's also how the hydrogen leaves and goes off to be a positive charge. All right? There's another example of what we're doing. Let's do another example. Again, one more after one more after one more. But I think it's good for you. Do you like that awkward silence? It's kind of weird, isn't it? I'm thinking. I'm thinking about structures. That's what I'm doing. Okay. So let's take a look at this particular type of compound. And let me just kind of finish it up here, give you all the information that you need to make these decisions. And I'll do it here. Leaving off dots, I'm good for that. Okay. So if we look at the left hand and the right hand side, we need to kind of show the flow of electrons just like we did before. So let's take a look at what's actually happened here. So I'm going to look at the arrow and I'm going to compare what was before to what's after. So one of the things that I do see is that the oxygen here, this OH group, has now been attached to this molecule. I see it here, pointed down toward the very bottom. Okay, so there's a very good sign. It's a place that I could start at least. This OH group with that negative charge, this is a negative source. I start the arrow here, and I'm going to point it to where it goes to, and that's to that carbon, because that's where it's got attached into the products. I also know that that carbon's slightly positive. How do I know that? Because carbon and oxygen has an electronegativity difference, and oxygen is more electronegative than carbon is. So it's an electron sucker, and that oxygen that's also right beside of carbon is also sucking electrons away from it as well. So it's got two suckers on it. Imagine dating two people at the same time and they both demand every dollar and cent that you have. You're going to be broke, and that carbon is broke. So that carbon is highly exposed as far as partial positivity goes. So that O that's negative is attracted to that oxygen that's already positive, and we begin to form a bond. The problem, though, is that this carbon already has 4 bonds, doesn't it? It's got 1 to the methyl group, it has 1 to the right-handed oxygen, it's got 2 to the oxygen up above. So there's a total of 4 here. In order for that carbon to take on that OH, that carbon has to make a decision to say, you know what, I've got too much now. I mean, I can't take another relationship on. I'm already in a relationship with 2, and now you want me to be in a relationship with 3? And the answer is, yeah, kind of. So it's got to make the decision to cut ties with something. What it decides to do, look up here at the very top. There is a double bond, but now there's just a single. Okay? There's just a single right here. And actually, I forgot to write another set of electrons. It's going to be here. All right, sorry. All right, so this double bond has now turned to a single. Where do those electrons go in that double bond? Well, this oxygen had 2 sets of electrons, and over here it has 3 sets. Well, that third set, it's going to come from one of those bonds between the carbon and the oxygen. So this is a two-stepper. A two-stepper curvy arrow. The first one represents oxygen coming into that carbon. That carbon's overloaded at this point, too many bonds. Now the carbon decides, oxygen, you got to take them. You got to take some of these because I need that 4th spot opened up, and you're electronegative. You want them anyway, so take 2 of those electrons from that double bond and suck them on up. And that's what that oxygen does, but in doing so, it becomes a negative at this point. Once again, just another way to write a curvy arrow mechanism, and that's what this is all about. All right, so that's where this video is going to stop. Next video, I'm going to do a more formal example. We're going to work through a couple of more of these, just so you get the hang of it. That way there's no curveball or tricks up my sleeve, and then we'll finish out the lecture material. Almost done. Almost.